Oh, sorry. I didn't, yeah. Okay. So this was my y predicted in logistic regression. Okay. So this was my y predicted. And what do we call this function? 1 upon 1 plus e to the power minus x or minus z we can take. What do we call this function? Come on, I guess I told you last time. What do we call this function? Okay, so this is known as sigmoid. Okay, sigmoid function. So in logistic regression, my y predicted is this. And if we will calculate the cost function, okay, so what will be my cost function? 1 upon m summation I equal to 1 to m, okay, uh, y minus y predicted whole square. Okay, so this will be my cost function for logistic regression, correct? So do you think that the curve or the curve for this cost function would, like, what would be the, like, how will be the function? Like, can anyone of you tell me, will it be like this? Will it be like this? Here I will have my weights, here I will have my error. So do you think that the curve will be like this?
No, sir.
Why?
Mm,
You're
it
correct,
will
but
be,
why?
I think, z reverse form.
Mm-hmm.
Means,
Because, like, where is this w coming? Okay, I'll okay, I will write this. Okay, I will write this in the form of matrices now. Okay, so don't get confused in that. I will write like this: 1 upon 1 plus e to the power x theta. Okay, in this way I'm writing. So okay, so this is the problem. This is the problem. Earlier this y was simply na mx plus c. Earlier this y was simply mx plus c, but now this is not mx plus c. Now it is 1 upon 1 plus e to the power minus x theta. So that's why this cost function, okay, this cost function will not be convex. Okay, this cost function will not be convex, so I will not be able to converge. Okay, so that's why I will not be using this cost function. Okay, is it clear that why I'll not use this cost function? Because like, now we have sigmoid over here, so the curve okay, so the curve will not be this parabola. Okay, so we'll use a different cost function. Okay, so we'll use log likelihood function. Okay. For measuring the cost, I will use this function, log likelihood function. Okay, so I will write like this. This will be minus yi log of, okay, predicted value, okay, 1 minus yi log of 1 minus pi, and write like this. And like, let me make it a little bit simpler. I will plus summation I equal to 1 to m 1 upon m. Okay, so I'll write like this: j of theta I will write. Okay, so this theta I'm referring as the weights. Okay, this theta I'm referring as the weights. Now you would be scared by looking at this equation, but there is no need to be scared. Okay, it's like very easy equation. Okay, so I would like to ask you one thing, that suppose my actual output, okay, y actual and y predicted. So these are my y actual and y predicted. So suppose this y predicted came out to be like, if this is 1, okay, so then y predicted is 0 0.2 and 0.8, okay, 0. So it is 0.1 and uh, 0.6, okay. So if my y is 1, okay, so then which y predicted should I use, 0.2 or 0.8?
0.8.
Why?
It is very close to 1.
It is very close to 1, but when it is 0, then which one should I use?
0.1.
0.1. Why? Because it is close to 0, correct? So if my output is 1, okay, then I want that the probability should be as close to 1. If my probability is if my actual is 0, then I want the probability as close to 0, okay. But what I calculate using my like in pi, okay, what I calculate, I like, we can consider anything also, like generally we calculate the probability of 1. What is the probability of this y to be 1? This I calculate, okay. So like this is the actual value that I calculate, probability of 1, probability of 1, okay. So if we talk about this term, if the actual is 1, then what I want to maximize, okay, I want to maximize, see, I'll write 1 into log of 0.2, okay. Okay, and why I have used logged over here, because for like, if it is, if the value is less than like 0, sorry, if it is in the fraction part na, then this log will magnify this value, okay. Like if the value is like this, if the value is like this, log of like, if the base is 10, okay, 3, okay, so what will be the value of this, log to the base 10, 10 to the power 3, what will be this?
3.
Correct, correct. Yeah, it's 3, 3 log 10 to the base 10 will become 1, okay. So this one will come forward, correct. If it is like this, log 10, okay, 10 to the power minus 2, so what will happen, what will be the value of this, negative
Minus
2,
2.
negative 2, okay. So so this 10 raised to the power minus 2, it is less than 1, and it is between 0 and 1, okay. So what is this in reality, what is this, it is 1 upon 100 na, so 1 upon 100 is 0.01, okay. So this I can write it as 10 to the power minus 2. So okay, so I am interested in this power, okay, I'm interested in this power, so that's why I have taken the log, okay. So what will it do, it will magnify the value of this, okay. So that's why I have taken the log, because it is between 0 to 1. If it is, the value is between 0 to 1, then log will magnify its value, okay. And if it is greater than 1, then it will reduce its value. So you can see that 1000, 10 raised to the power 3 is 1000, okay. So when I took the log of this, then it became 3, okay, and here it became minus 2, okay. So okay, like here but the value that will come out na, if it is between 0 to 1, it will be negative, okay. So in order to make it positive, I multiplied the minus sign, okay. So this was for my the positive examples that I have, okay, for which the actual is 1. But if the value is 0, then how will I write, can I write like this, 1 minus 0,
There was 3 is not visible to.
okay, okay, for this 0 part, okay, if the actual output is 0, then I will write like this, okay. Because here what I want, the probability of 0 to be maximum, not probability of 1, है ना. Here to like what I am calculating, the predicted is actually probability of 1, but in this case, I want the probability of 0 to be maximum. So what will be the probability of 0? It will be 1 minus probability of 1. Okay, it will be 1 minus probability of 1. So that's why I have written 1 minus probability of pi, we can write. Okay, pi, 1 minus pi. Okay, so that's why I have written like this. So if my y is 1, okay, if y is 1, then this term will vanish. This term will vanish. Okay, if my yi is 1, then which term will vanish, this one or this one? Now please tell, if yi is 1, which one will become 0? If yi is 1, which term will go away?
Second term will go
Second
away.
term will go away, na? Because my actual is 1 and the probability that I'm calculating is also of 1. Na? Probability that I'm calculating is of 1 only. So that's why I don't need this probability of 0. Okay. But if my actual output is 0, then this term will go away. This will become 0. So this whole term will become 0. So here, I'm not concerned about this now. I'm concerned about the probability of 0. So this is the probability of 0. Okay, and 1 minus y, why I'm using 1 minus yi, so that this term remains. Okay, 1 minus 0 will become 1. So that's why I have written the equation like this. Okay, so I hope that you would have understood what is the meaning of this equation. Okay, so like, is this clear, that equation that we have written? Like, have you understood the meaning of this equation, why I have written the equation like this? Okay, so this is known as the log likelihood function. Okay, I want to maximize the probability of 1. Okay, I want to maximize the probability of 1. Okay, for those points only whose actual output is 1. Okay, and I want to like increase the probability of 0 for which the actual output is 0. Okay, so like, I hope you would have understood this. Okay, so that was the intuition behind this long equation. Now what will we do? We'll write this equation again, and like, suppose, like, before writing this equation, okay, let's try to find the derivation of the sigmoid. Okay, let's try to find the derivation of sigmoid. So we'll write like this: p of xi equal to 1 upon 1 plus e raised to the power minus xi theta. Okay, this I'll write. So if I will differentiate this with respect to theta, okay, so what will be the derivative? Okay, so first I will consider this term as x. So first 1 upon x. Okay, so I will consider this term as x. So what will I do? What is the
Log x.
difference? Huh?
Oh, I think
No, this will not be log x. This will not be log x. I guess the integration of this is log x, but not the differentiation. No? It will be x to the power minus 1. No? So what will I write? Minus 1. Like, the differentiation of x to the power minus 1 with respect to x. What will be it? Come on, x to the power like minus 1. X to the power minus 1 minus 1. That means x to the power minus 2. है ना? Minus 1 upon x square. This will be the derivation, like differentiation. Is it correct? What is the formula for the differentiation? X to the power n. What is the formula for like differentiation? N into x to the power n minus 1. No? Okay, so dy dx is n into x to the power n minus 1. So here the power is minus 1. Okay, so minus 1 will come in front, and we'll subtract 1 from the power. So it will come like this. So we will do like this. Okay, I'll erase this part. Okay. Like you may be thinking that why I'm teaching you all these things, but like if you will study like this, then you will be able to understand like much more about the machine learning, because I can like directly tell you the code that you can use this library and do the coding. Okay, like you can just implement them, but you will not be able to understand the intuition behind it, like why they are doing these things. Okay, and in like industry also, sometimes you have to implement the algorithm by yourself. You will not be using these sklearn, okay, libraries for implementing your model. So that's why like it's always better to know the derivation of each algorithm that we have studied. Okay, so that's why I'm telling you all these things. But like if you want to just focus on the implementation part, that is also fine. But like if you will study these derivations, then the things will be more clear to you. So that's why I'm telling you all these things. Okay, so the derivation of this will be 1 upon 1 plus e to the power minus xi theta whole square. Okay, so this term I have differentiated. Now I will differentiate this term. So the differentiation of e to, what is the differentiation of e to the power x? What is the differentiation of e to the power x? Okay.
E for x is E for x.
Okay, it will remain same. Now I'll find the derivation of this part. So what will be the derivation of this part? Xi theta minus xi theta. Okay, so it will be minus xi only, because we are differentiating with respect to theta. No? So this theta will vanish and only xi will remain. So this minus minus will become positive. Okay, minus sign will come in front and it will become positive. Okay, now what will I do? I'll rewrite this equation in another way. I'll write like this: 1 upon 1 plus e to the power minus xi theta whole square. Sorry, I'll remove the whole square. Okay, I'll divide this like this: e to the power minus xi theta whole upon 1 plus e to the power minus xi theta into xi. Okay, this square term I have divided. Okay, I have divided into two parts, this part and this part. So now I'm taking this part only. Okay, so see this part. What is this part? This part I can write p of xi. You know, this is same as p of xi. So I'll write p of xi over here. Correct. And what about this part? Okay, what about this part? So let's try to find 1 minus p of xi. Okay, let's try to find 1 minus p of xi. What will be 1 minus p of xi? 1 minus 1 upon 1 plus e raised to the power minus uh, minus xi theta. Okay, I'll take the denominator common. So it will become like this: 1 plus e raised to the power minus xi theta minus 1 whole upon 1 plus e raised to the power minus xi theta. So 1 and minus 1 will get cancelled. So this will become e raised to the power minus xi theta whole upon 1 plus e raised to the power minus xi theta. Correct? So 1 minus p of xi will become this. And this is the same term that we have over here. Correct? No? So we will write like this. In place of this, I'll write 1 minus p of xi into xi. Okay, so this is my differentiation of the sigmoid that I have. Okay, so this is the differentiation of the sigmoid function that I have, but this is not the actual derivation that we need to do. We need to apply the derivation on the cost function. Okay, so let's see. Okay, so the cost is negative 1 upon m. Okay, summation yi log p of xi plus 1 minus yi log of 1 minus p of xi. Okay, now what will I do? I will just take this term. Okay, this term. and I'll try to I'll find the derivation of differentiation of this. Okay, so I will do the differentiation of this cost with respect to the theta that I have. So it will be 1 upon m, okay, summation del theta, okay, yi log p of xi plus 1 minus yi log 1 minus p of xi. All right, now I will just differentiate this part. Okay, okay, I'll be differentiating this part, and we'll see how we will be differentiate. So can you tell me what will be the differentiation of this with respect to theta? Okay, so uh, like in which term the theta is present? Like we cannot see theta over here, no? But in which part theta will be there? Will it be present in the yi? Will theta be present in the
No,
yi?
no,
In
no,
which
sir.
term?
It will
In which
be
term?
P of xi.
Yeah, p of xi, na? So okay, only p of xi will be dependent on theta. So all other terms that we have, that will remain constant. All right. So let's see. So the differentiation of first part, we'll see only this part. Okay. What will be the differentiation of this part? Yi. What is the differentiation of log x? Okay. So for log x, we have differentiation 1 upon x. Okay. So it will be 1 upon p of xi. Okay. And we'll find the differentiation of inside part also. So this one I'll write as p dash of xi. Okay. So I will write like this, and I'll find the differentiation of other part also. So this will be 1 upon 1 minus p of xi, okay, multiplied by what will come? What will be the differentiation of inside part? Negative p of p dash of xi. All right. Now I will, okay, I have found the p dash of xi. Okay, I found the value of p dash of xi. What was that? Okay, so this is p dash of xi. So this I have found p of xi, 1 minus p of xi into xi. Okay, I will write over here yi whole upon p of xi, okay, p of xi, okay, 1 minus p of xi into xi, okay, and here also 1 minus yi whole upon 1 minus p of xi, okay, okay, and negative sign, okay, I'm keeping it over here, okay, negative sign, and I'll write p of xi, okay, 1 minus p of xi, okay, into xi. Okay, so just see, this term will cancel and this term will cancel. Okay, now now let's see what will be the output. So it will be yi, okay, 1 minus p of xi, okay, because xi is common in both the terms, so I will take xi common, okay, plus this will be 1 minus yi, okay, I'm taking this negative side inside, okay, so negative p of xi, okay, and this xi na, I'm taking it as common, okay, because this is present in both the terms. Now let's try to simplify the inner term. Okay, so it will be yi minus yi into p of xi, okay, negative minus p of xi plus yi into p of xi, okay, into xi. Okay, so this two terms will be cancelled. Okay, so I will be remained with this one only, p of xi, okay, into xi. Okay, so this is my final derivative that I got. Okay, so this thing I will be replacing in this part. So what will be my final answer? Okay, final answer will be del of cost whole upon del of theta is equal to negative 1 upon m. Okay, summation yi minus p of xi into xi, yeah, equal to 1 to m. So this is my final, okay, final
Sir,
answer. Yeah,
why that negative sign in front of that minus 1 by m?
yeah, it was minus 1 by m, no, earlier only in the cost function only it was negative 1 by m. Like
Not
I,
likelihood function in that also it will minus
eh?
1 by m.
Ha. In low likelihood also, no, it was 1 by m, like I told you, no.
Yeah, okay.
Oh, sorry. I didn't include this negative. Yeah, it will be negative because we are taking the log, no, and the probability will be between 0 to 1. So the value will be negative. So in order to make it positive, uh, people have left, huh? Okay, no problem. I think you are tired of all these things, but like just bear with me, okay? We are about to finish. So this is the final output that I got. And sorry, like it was actually negative 1 upon m, okay? Negative 1 upon m. So this is the actual derivative that I have got. Okay. Now, okay, the now the dimension of yi will be, if the number of terms are m, so it will be m into 1. Okay, so this one should also have m into 1 number of terms. All right, and okay, because we'll be adding this with the theta. Okay, so theta equal to theta minus alpha into del cost by del theta. Okay, so the dimension of this will be, okay, the number of features that I have plus 1. Okay, so if the number of features are n plus 1 into 1. Okay, so this will be the dimension of this. So the dimension of this should also be n plus 1 into 1. Okay, so how will we make it like this term? Okay, the dimension of this term should be n plus 1 into 1, this whole term. Okay, till cost. So the dimension of xi will be, okay, uh, m into, okay, m into n of m into n plus 1. Okay, so these are the number of rows and these are the number of columns, and y plus 1 because we have added one column for the bias. Okay, so let's see. So then what will happen, that for this del cos, this is cost. Okay, why I'm writing theta, I don't know. Del theta, this will be minus 1 upon m. Okay, I will write x transpose over here, x transpose minus yp of xi. Okay, negative 1 upon m, and like summation we can use. Okay, so why I have written x transpose over here, because so that they can multiply with each other. Okay, so because it is it x transpose dimension will become n plus 1 into m, and this dimension is m into 1. Okay, so when we will multiply, the dimension will become n plus 1 into 1. So like this is the updation equation that we will be using, and let's try to see the code of this. So what I have done, I have used this function, okay, from this sklearn.datasets. Okay, so here I have specified the number of samples, features. Okay, and I don't know about these because I use this from some other code. Okay, for finding the data. Okay, and random state, so you know that the same data will be generated every time I run the code. If I don't specify the random state, then different data will be produced. Okay, So I will plot the data. Okay, so there are two features in this. Okay, so the dimension of my x is 2 into 1, and you can see that these are my blue point, these are my yellow, so I need to draw a line in between of them. Okay, so I will define a sigmoid function. So sigmoid of x will be 1 upon 1 plus e, okay, e to the power minus x. I will also be defining the theta. Okay, so theta, I have told you that it will be x transpose into y minus sigmoid of x. Okay, so like this is the delta equation that we will be using. One second. Okay, and this is my cost function. Okay, so what I am doing for the true values, okay, for true values I am calculating the cost, and for false values I am calculating the cost. Okay, so you can see that for true value I am calculating yi. Okay, okay, yi into uh, oh, I think this has become a little bit complicated, but okay, if you see the equation, then you will understand that this is the same thing I'm doing. Okay, see, this is yi. Okay, and this is the log. Okay, and this is of p of xi. Yi log p of xi. This is p of xi. 1 minus yi log 1 minus p of xi. Okay, so then what I'm doing, I'm adding this true and false, and then I'm multiplying it with by minus 1 by m. Okay, I'm doing the sum, and then I'm multiplying it by minus 1 upon m. Okay, so this is the functions that I have defined. Then in x, what I have done, I have added 1 into the starting column. So okay, I've used this h stack function, horizontal stack. So and theta I have defined, okay, 3 into 1. Why I have defined 3 into 1? Because the number of features are 2. Okay, and 1 will be used for the bias. Now I have defined the learning rate. Okay, and the theta shape is 3 into 1. Now what will I do? I'll use this cost. Okay, I'll use this find cost function. It will find the cost, and I'll use this delta. Okay, so delta is the same that I have told you, but in delta I also have to divide by m. So like it doesn't matter like if you divide by m or not. Okay, if we divide by m, then the number of iterations will be little bit low, but if you don't use m, okay, in the cost function, if you don't use divide by m also, so that will not matter that much. Okay, so we'll do like this, and for theta I will be using this equation, theta equal to theta minus learning rate into delta. Okay, so like I have already run this code. So like this is the classification report which I have got, and this is the score that I have got. Okay, so if my y predict is equal to y, okay, then it will mark it as 1, and I will divide it by the length of y. Okay, so using this I will be able to get the score. So I have got 96.6 score over here. Okay, so like it's a pretty good accuracy. Okay, using this model that I have got, and like I have drawn a line. Okay, between these two data sets. Okay, but the thing is the slope. Okay, in the weight section, okay, in the weight section we will have three values. Okay, so m1 and m2, and this will be my bias, but it is drawing this line in 2D plane. Like I don't know how it has drawn. Like this code I have copied from online. Okay, like I don't understand how it is able to draw this, but the main part is this, that the gradient descent, how we are using gradient descent in this. So this part, like I have written it myself, and I have used the same things that I have told you in the derivation. Okay, so I guess like just try to see the code, this code by yourself. Okay, how this is running, and where we are using transpose. Okay, and this at the rate means that I'm doing a multiplication of these two matrices. Okay, at the rate we can also use at the rate. Okay, so like, don't need to confuse like why this at the rate is being used. Okay, and like you would be wondering that why this dot reshape I'm using. Okay, dot reshape. Okay, because like you try to see that why I'm using this dot reshape. Okay, you just try to see that why I'm doing this reshape, and maybe later I'll tell you that why we have used this. Okay, all right, so that was it in this like logistic regression. Like do remember the like derivation that I have told you, because like by it is not very easy, okay, to get this derivation. Okay, it was like quite difficult for me to figure this out, and in internet also the equations that they were telling me was quite complex. Okay, so like somehow I found the derivation, because like if I'm not able to do the derivation, then I could not have told you, okay, all these things. But finally I was able to do it, and then I told you this thing. Okay, so it's better like do this derivation by yourself, then you will understand it much better, and try to code. Okay, this, okay, try to see everything that is inside the code. Okay, why, like how this matrix multiplication is being done, because this thing I've told you, na, bias and all, so like you will forget after some time. So if you code it by yourself, then like you will remember the things. Okay, all right, so that would be it in this session, and tomorrow we will be studying the knn classifier. Okay, so that the k nearest neighbor is also one of the algorithm for doing the classification. Okay, all right guys, so that would be it in this session. Thank you all for participating, and we'll meet tomorrow. Okay, till then, bye bye.